This is the first video lecture for the last unit of our course. In this last unit, we're going to be talking about counting and probability. And when I say we're going to be talking about counting, that might sound kind of silly for a college level class, but what we're really going to learn are different ways to count the number of ways that something can happen without literally listing them all and counting them one at a time. And that's what this first section introduces us to, is one method for doing that in certain situations. The section is entitled The Fundamental Counting Principle. And the idea is something that you might already be familiar with. We start with a simple example of the fundamental counting principle, and then we'll expand to a general idea here in a little bit. This first rule, which you can find in your handout, says if you can choose one item from a group of m items and a second item from a group of n items, then the total number of two item choices is m times n. Maybe that's not clear, but that's multiplication between those two. So if there are m ways that the first of two things can happen, and there are n ways that the second of two things can happen, then the total number of possibilities is m times n. You multiply those together. Before I do any examples from the book, I want to show you guys an example that's actually ringing true to me right now, and that's the number of wardrobe options that I have for my lectures. So since this stay-at-home order has been in place, I've given almost all of my video lectures wearing pajama pants and a hoodie. I'm doing it right now. And I've got three choices for pajama pants. I've got these plaid ones that I'm wearing right now that I kind of like. I've got these old gray sweats that actually have the Parkland logo on them that are kind of cool. And then I have these ugly striped ones that my wife bought us all for Christmas so that we could have matching pajamas. And I would never let anybody see me wear those in public. But to lecture, it's not a big deal when you can't see me. And then I have four hoodies. You may have seen me wear some of these to school. I have a red one, a green one, a gray one, and a blue one. Right now I'm wearing the red one with my plaid one, and it doesn't match, but again, it doesn't matter because you can't see me and because I'm a math teacher, so I'm supposed to look like a dork. But anyway, so how many total wardrobes could I wear for my video lectures? Well, I've already started what we call a tree diagram to lay this out. I've got the plaid, sweats, and striped options for my pajama pants. And then with each of those, there are four possibilities for what I could match with those. So I could wear the red, the green, the gray, or the blue with my plaid. I could wear the red, the green, the gray, or the blue with my sweats. And I could wear the red, the green, the gray, or the blue with my striped. And if I count up how many options I have, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total ways that I could make a lecture wardrobe for my pajama pants and hoodies. Now, you might immediately see that there is a faster way to do this, and that's what the previous rule is telling us. If I can choose one of three pairs of sweats and one of four different hoodies, then the total number of two item choices I have is just 3 times 4. There were 3 possible pajama pant options, there were 4 hoodie options, and that's a total of 12. So rather than counting out the number of ways this can happen by making a tree diagram or doing something similar, listing all of the possibilities, I simply could have multiplied the number of options for the first choice by the number of options for the second choice. And this is a specific case of what we call the fundamental counting principle. So let me demonstrate this with a couple of examples from the book. These won't be any more difficult than the pajama one, but here we probably won't want to make a tree diagram because the number of options will just be too large. So my first example comes from page 286 of the softcover book, the Parkland edition of the book, and we'll just start with problem number 1. It says, a restaurant offers 8 appetizers and 10 main courses. In how many ways can a person order a 2-course meal? So the person ordering a meal has 2 choices, and I'm going to represent these with blanks. I don't require that you draw the blanks, but I think it's a good idea, especially as the problems get more difficult, to give yourself a blank for each of the choices or options that you have. It says that there are 8 appetizers to choose from. So assuming you're ordering the appetizer first, you have 8 options in the first blank for the appetizer. And then there are 10 main courses that you can order. So there are 10 options there. And if we're going to order those in succession, then the total number of options would come from multiplying. That's what that rule on the first slide said. If you have m ways to choose from the first group and n ways to choose from the second group, then the total number of 2 item choices is m times n, so we would multiply. 8 times 10 is 80. And so there are 80 possible meals that you could order with an appetizer and a main course. Pretty straightforward, not too difficult. Number 6, same page. For a temporary job between semesters, you're painting the parking spaces for a new shopping mall with a letter of the alphabet and a single digit from 1 to 9. In the book problem, they actually give examples of this. I kind of cut down the problem just to fit it on my slide. How many parking spaces can you paint with distinct labels? So when they say distinct, they mean they have to be different. So let's see, we're going to make 2 symbols on the parking space. We're going to put a letter of the alphabet in the first blank, and we're going to put a digit from 1 to 9 in the second blank. This might not be common knowledge, but there are 26 letters in the English alphabet. That's something you'll need to use from time to time on the problems in the book. And then if you have to choose a single digit from 1 to 9, well, that's 9 choices there. So this is 26 times 9, which I believe is 234, but I'm going to double check that with the calculator here. 26 times 9. Okay, good. So 234 total parking spaces that you could label with this procedure. So this probably isn't something that will ever come up in your life, but the idea you can imagine is something that's useful in the real world. Suppose you're trying to come up with a system for enumerating parking spaces or spots like cubicles at a job or something like that, and you're trying to come up with a coding system. And if the options that you have are smaller than the coding system that you're using, that's fine. But if you have more options, like suppose this shopping mall had 360 parking spaces, well, then this coding system isn't going to work because it can only do 234 total options. And so this is stuff that people have to think about in the real world. Maybe you don't find it very interesting in this specific example, but it's something that people have to do. All right, let's generalize here. Rather than just looking at 2 options, we can extend this to any number of options. This is what we call the fundamental counting principle. We sometimes abbreviate it FCP for short. The fundamental counting principle says the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. So that's what the first rule basically said for 2 items. If you have m ways that the first thing can occur and n ways that the second thing can occur, then the total number of 2 item choices is m times n. The new rule, the fundamental counting principle, just extends this to any number of choices. You find the number of ways that the first thing can occur, the number of ways the second thing can occur, and just keep stringing that out till you get to the last item, and then just multiply those all together. Same idea, just more choices. So let's look at some examples from the book. Problem number 8 on page 287 says a pizza can be ordered with 3 choices of size, and in the book I believe they give you the different sizes, but I didn't put that here. 4 choices of crust and 6 choices of toppings. And again, I think it lists the choices of crust and toppings, but I didn't list those here because that's not important for the problem. The question is how many 1-topping pizzas can be ordered? And the fact that we can only choose 1 topping is what's going to make this just a fundamental counting principle problem. It'd be a little more difficult if we had to consider all of the various topping choices. But with just 1 topping choice, this is a straightforward problem. So there are 3 choices to make, so I'm going to draw 3 blanks. 1 for the size that we're going to choose, 1 for the type of crust, and 1 for the topping that we choose. So we have 3 choices for size. We have 4 choices for crust. And if we can only choose 1 of the 6 toppings, and we're going to choose 1 of the 6 toppings, then there are 6 choices for the 1 topping. If we would allow for 2 toppings or all 6 toppings or no toppings, then this number would be a little more complicated to figure out. But if we're requiring a 1-topping pizza, then we have 6 choices. We're going to pick 1 of the 6 toppings. And then we multiply this together. 3 times 4 times 6 is 72. And so there are 72 1-topping pizzas. If you're interested, you can go back to the material that we learned in Chapter 2 about the number of subsets to figure out the total number of pizzas that can be ordered with any number of toppings. I'm not going to bore you with that here. but if you're interested, you can shoot me an email and see if you got it right. I'm going to move on to the next one. Number 15. You're taking a multiple choice test that has 5 questions. Each of the questions has 3 answer choices with 1 correct answer per question. If you select one of these choices, 3 choices for each question and leave nothing blank, in how many ways can you answer the questions? So the difficult part of doing these kind of problems is figuring out how many blanks there are and what goes in the blanks. So you need a blank for each choice that you have to make. Not each choice that you have, that's what goes in the blanks, but each choice that you have to make. You're taking a test that has 5 questions, and each of those questions requires you to make a choice. So you need 5 blanks for the 5 questions. Each of those questions has 3 choices that you can make. And so that's 3 choices for the first question, and 3 choices for the second question, and 3 choices for the third question, and for the fourth and for the fifth. The reason why it was important that we're going to select it 1 and not more is that we don't have to do any calculating for how many different ways we could choose 2 or 3, all 3 options. And leaving nothing blank means that we have exactly 3 choices. There is a 4th choice to just skip the problem, but we're not counting that here. We're just going to go with the number of ways that you can actually answer all 5 questions. So 3 times 3 times 3 times 3 times 3 is 243. I would encourage you, when you use your calculator, to take advantage of repeated multiplication by using exponentiation. So 3 times 3 times 3 times 3 times 3 is 5 copies of 3. So you can hit the caret key and give yourself an exponent in order to get that answer. So there are 243 different ways that you could answer those 5 questions. So we'll talk about this more later, but one of the reasons we would want to calculate this is to find the probability that you could guess all of the right answers. So if there are 243 total ways that you could answer the questions and only 1 correct answer per question, then the probability that you guess all 5 correct answers without putting any thought into it, literally just guessing, is only 1 in 243. It's very, very rare to guess all 5 correct answers. It just wouldn't happen very often. 243 possibilities and only 1 way to guess all 5 right answers. That comes out really close to 0.4%. It's less than 1% of the time. That's the kind of stuff that math people would use this for, find probabilities. Number 17. In the original plan for area codes, the area code is the first 3 digits of your phone number. So like the area code we live in right now is 217. The first digit could be any number from 2 through 9. The second digit was either a 0 or a 1. And the third digit could be any number except 0. With this plan, how many area codes are possible? So there are 3 digits in the area code. So there are 3 choices that have to be made. 1 for the first digit, 1 for the second digit, 1 for the third digit. And then in the blank, we're going to write the number of options we have for each of those. So the first digit could be any number from 2 through 9. Be careful about this. We had to talk about this when we were doing the credit card problems. The number of digits from 2 to 9 is not 7. You can't just subtract those. If you go ahead and count them out, you'll see that there are actually 8 numbers from 2 through 9. 2, 3, 4, 5, 6, 7, 8, 9 is 8 digits, not 7. You can't just subtract. When you subtract, it leaves out one of the edges. So there are 8 options for the first digit. The second digit was either a 0 or a 1, so that's 2 options. The number of options goes into the blank. I'm not going to use either of those numbers. I'm going to use the total number of choices. I have 2 choices. And the third digit could be any number except 0. And when they say number, they mean digit. So those are the digits from 1 to 9. So there are 9 options there. So the total number of possible area codes would be the product of those 3 numbers. That's what the fundamental counting principle tells us. 8 times 2 is 16. 16 times 9 is 144. And so there are 144 area codes possible with the original plan. So again, if the number of area codes needed in the United States went beyond 144, then they would have to extend the rule. This rule would not suffice if we wanted more than 144 area codes. Let's go on to the next one, problem number 20. Same page. How many different 4-letter radio station call letters can be formed if the first letter must be W or K? I assume this rule is still true. I don't know for a fact. But it used to be that if a radio station was on the east side of the Mississippi River, then that station's call letters would begin with a W. And if you were on the west side of the Mississippi River, then the call letters would begin with a K. I don't know if that's still true, but let's just run with this using this rule here. How many different four-letter radio station call letters can be formed using this restriction on the first letter? So there are four choices we have to make, one for each letter. We need to choose the first letter, the second letter, the third letter, and the fourth letter. And my advice when there are restrictions like this is to start with the spot with the restriction. So there's a restriction on the first letter. We have two choices for the first letter. So I'm going to fill in the first blank with a 2. There are no restrictions on any of the other spots. It doesn't say that we have to restrict the second, third, or fourth spots like we did in the previous example where there were restrictions on every spot. So we can choose any letter we want in the second spot, so there are 26 options there. And it doesn't say we can't repeat letters, so we still have 26 options in the next spot and 26 options in the last spot. So this is 2 times 26 times 26 times 26. And again, I would encourage you to use exponents here to shorten this up. I'll do it both ways. So you could literally just type 2 times 26 times 26 times 26. So there are 35,152 options here. Or you could type 2 times 26 to the third power. And the reason why I want you to get used to the exponents is if we have more than 3 options, like suppose there were 8 more spots there, the exponent's going to be a little bit more convenient. You're less likely to make a silly mistake by leaving out one of the factors or putting in an extra factor. So the exponents are kind of nice for that. Either way, we get 35,152. 35,152 total 4-letter radio station call letter combinations that we could make using this restriction on the first letter. One more. This one's kind of difficult. It's on page 288, problem number 30. It says, how many 4-digit odd numbers are there? Assume that the digit on the left cannot be 0. So we've got 4 digits in our odd number. And it says that we can't form a 4-digit number using a 0 on the left. So there's a restriction in the first spot, and there's going to be a restriction on the last spot. And this is the hardest part of this problem, is figuring out the restriction on the last spot. Let me start with this first spot. If the digit on the left can't be 0, then the first digit can be anything from 1 to 9. And so you've got 9 options there. In the last spot, there's a restriction on that last digit. I know you guys know this rule, but when you're trying to use it in combination with a more complicated problem, it might slip your mind. If a number is odd, then the last digit has to be an odd number. So let me give you some examples of some 4-digit numbers, like 4627 or 3583 or 9191 or 6375. These are all odd numbers, but none of the digits on the left side of the last digit matter at all. It doesn't matter. You'll notice that in this first example, I made all of the first 3 digits even. The last digit was odd, but that makes the entire number odd, because a number is odd if and only if its last digit is odd. And I've listed 4 of the possibilities here. So let me just put one more up here. 2229, that's the 5th odd digit that we could have in the back. As long as the last digit is a 1, a 3, a 5, a 7, or a 9, the number will be odd. So we have 5 choices for that last digit. We can't choose 2, 4, 6, 8, or 0 in the last spot, because if the last digit is even, then the number is even. So we have 5 options for that last spot. There are no restrictions on what the second number could be. The second number could be even, it could be odd, it could be 0. I didn't give an example of that, but the number 7005 is an odd number. Doesn't matter that these are even numbers, so we could pick any of the 10 digits, including 0 for the second. We could pick any of the 10 digits, including 0 for the third. And so we have 9 choices for the first digit, because it's not allowed to be 0. 10 choices for the second and third digits. because there's no restriction on those. And the last digit has to be one of the 5 odd numbers, and so we only have 5 options there. So we have 9 times 10 times 10 times 5, which is 4,500. You would get the exact same answer for the number of possible even 4-digit numbers, and it makes sense there are just as many odd 4-digit numbers as there are even 4-digit numbers. That's the end of the examples for the fundamental counting principle. I strongly encourage you to try some of the problems in the book. Remember that all of your test questions come from the book, so the more problems you do, the more likely you are to be prepared for the exam. If you have any questions for me, send me an email.